Right, this is part 2 of the notes we did on Wednesday. And we started off with solutions. It's a homogeneous mixture of two or more substances that are in a liquid phase. Now, the solvent is the dissolving medium, otherwise known as the thing that's doing the dissolving. This is usually the liquid. And the solute is the substance that's being dissolved, and this is usually going to be a solid. At this point, what we did is we stopped and watched a video, and you can find the video. It's in Edpuzzle. The link for it is in Google Classroom, and that was rate of dissolving. So if you haven't done that Edpuzzle, be sure that you've got that done. I did take a grade on that. All right, so agitation causes collisions between the solute and the solvent particles. You can increase the rate that something dissolves by changing the surface area. The more surface area, the faster it's going to dissolve. If you increase the temperature, remember kinetic energy is temperature. Ke stands for kinetic energy. An increase in temperature will increase a solid's solubility in a liquid. Now, this is not true for a gas. In fact, if you increase the temperature, it will decrease how much gas will be dissolved in a liquid. Let me do a little blow-up drawing here of that. So let's say I've got a glass of soda, and this one is cold, and I've got another glass of the same type of soda, and this one is warm. There's the level of fluid. And let's say that I've got carbon dioxide dissolved in there. That's what's going to give it the fizziness. In the cold, our particles are going to be moving slowly. They're going to bump into each other less often. And they're going to be able to get out of the soda more slowly. The rate that these are going to be leaving is going to be slower because the particles are moving slower. Also, if they're bumping into each other less, we can have more particles in here. Remember, these are gas molecules. In a warm solution, these particles are moving much faster. If they're moving much faster, they're going to bump into each other, and they're also going to reach the surface quicker. So these particles, more of them are going to leave. So when you're comparing cold versus warm, you're going to have a greater number of gas particles able to be present in cold versus something that's warm. Now, the other thing that makes a difference as far as what influences the rate of solubility is the substances that are involved. If they have weak intermolecular forces, they're also going to dissolve more easily. Solution equilibrium, the rate of crystallization, it's going to be reach equilibrium when the rate of crystallization and dissociation are equal. We can think of crystallization as being particles coming together or coming back together. Where dissociation is the separation of ions. Remember, ions are charged particles. So when we're looking at solution equilibrium, the rate that things are coming back together and forming a crystal is going to be equal to the rate that things are breaking apart, disassociating and separating into ions. An ionic compound is a compound that is made from positive and negative particles. Oops, don't cross the L. There we go. So NaCl is a good example of an ionic compound. When the sodium and the chlorine are bonded together, the overall charge is going to be 0. When they come apart in a solution, we're going to have sodium ions that are positive and chlorine ions which are negative. So NaCl is an ionic compound. When it's held together in a solid form, there's no charge on the particle. When it separates out, when it's dissolved in water, there is going to be charged particles in that solution. An aqueous solution is a solution where water is the solvent. Effervescence just means that it is fizzy due to the escape of gases. A surfactant is a substance that reduces the surface tension of a liquid. An example of this would be dish soap. That will reduce the surface tension of water and the other molecules that are in there, and so it'll break up oils. The next, more vocabulary words. A heterogeneous where particles in solvent are so large that they settle out is called a suspension. Muddy water is a great example. The soil is more dense than water, so gravity is going to pull the soil to the bottom. A colloid is a mixture formed from particles that are sized in between those of solutions and suspensions. The particles are small enough to be held throughout the solvent due to the movement of the surrounding molecules. And of course, solutions are going to be 2 or more substances, and that should be liquid substances, that will not settle out. Now, you can cross out these right here. We're not going to be doing any of that vocabulary. And moved back to, we started the POGL on solubility. So that's the next thing that we did. And that was the notes for Wednesday. All right, these are notes for Friday. And we're going to be, when you finished up yesterday, you were doing the POGL on saturated and unsaturated. And so we're going to continue the notes and go on to molarity and so on. So, unsaturated solution is a solution that contains, if I can get my thing to work here, contains less than a saturated solution under existing condition. It contains less solute than a saturated solution. A saturated solution contains the maximum amount of dissolved solute. So that's going to be the solid part. A supersaturated solution is a solution that contains more dissolved solute than a saturated solution contains under the same conditions. Usually these conditions, we're talking about temperature. So you can force a solution to become supersaturated if you increase the temperature, and when you do that, you're going to weaken the bonds or the intermolecular forces within the solute. Now, this can remain unchanged for a long time, but once crystals begin to form, the whole process is kind of like dominoes, one hitting the next, and the whole thing is going to crystallize out until you get to the solubility of the substance for the temperature that it's at. A really good example of this is those hand warmers. If you have the kind that has the little disc in it, when you snap the little disc, it sends a wave and disrupts the particles, causing them to settle out and turn into a solid. As it does, it releases heat. And you can actually recharge those by putting them back in boiling water. They'll turn back into a liquid. And then you cool it down slowly, and you can actually use those hand warmers over and over again. But that's an example of a super saturated solution. So molarity, you're going to use the capital M as an abbreviation for molarity. It's the number of moles of solute per 1 liter, and it's important that it's 1 liter of solution. So zooming in on this, concentration is usually going to be in moles. N, remember, stands for number of moles. And the V, of course, stands for volume. In the case of molarity, the volume is always going to be 1 liter. Now, the steps for making a solution, if you want a 1 molar solution of NaOH, the first thing you're going to need to do is we want 1 mole of NaOH, is you're going to have to figure out what is the mass of a mole of NaOH. So that means it's going to be in grams, so you're going to need to grab your periodic table and calculate the molar mass. So we have 1 sodium atom, that's 22.99. We have 1 oxygen, 16.00. And we have 1 hydrogen. Add that all together and you're going to get 40.00 grams per mole. So that's step number 1, is number 1, find molar mass. Since this is a 1 molar solution, I'm going to need 40.00 grams of NaOH. Step number 2, we're going to come on over here to our beaker. So number 2 is place desired number of moles in empty beaker. So in this case, we're going to put in this beaker 40.00 grams of NaOH, because we want a 1 molar solution, and 1 mole weighs 40 grams. Step 3 is add solvent to 1 liter. So we're just going to add our solvent till it comes up to, let's say this mark right here is 1 liter. And then we're going to stir it, mix it all up, and then we will have made a 1 molar solution. Now, it's important to do it in this order. It would be wrong to, by accident, do 1 liter of solution and then put your 40 grams of NaOH in it. Because you're going to end up, of course, if we add solid to a liquid, the level of the liquid is going to come up, and you're going to end up with more volume than what you need. You need to have exactly 1 liter. So you have to do this in that order, because it's moles per liter. All right, on to the next section. So immiscible. Immiscible are liquid solids and solvents that are not dissolvable. In each other. Example would be layers in Italian dressing, and here's another example right here. When we're focused in on this test tube, you can see that there's a line right here where the 2 different liquids are meeting, but they're not mixing. If you could blow this up, you see that there's a level right here where these molecules are not mixing at all. Now, the opposite to this is miscible. These are going to be liquids that dissolve completely in one another in any proportion. So here's an example of miscible fluids. You can see that the molecules are well mixed together. There's no line that forms. Okay, on to properties of water. We did a video where you answer some questions watching a video. So this summarizes that video. So polar, oxygen is negative and hydrogen is positive due to their differences in electron attraction and the molecular structure. So zooming in to our water molecule here, oxygen pulls electrons close to itself. And remember, electrons are negative. They're going to have a negative charge, which means that this whole side of the molecule is going to be overall have a negative charge. If it's pulling the electrons to itself, it's pulling them off of the hydrogens, which means the hydrogens are going to be slightly positive. So this whole side of the molecule is going to have a slightly positive charge. And that's what we call something that's polar. Hydrogen bonding is the intermolecular force in which a hydrogen atom is bonded to a very small, highly electronegative atom like nitrogen, oxygen, or fluorine. Zooming into this, here's a water molecule, and here's another water molecule. This area in between here is the hydrogen bond. Because the hydrogen side has a slightly positive charge and the oxygen side has a slightly negative charge, those are going to be attracted to each other, and that's what's going to form this attraction. Think of it as two magnets that are going to kind of lock onto each water molecule. So that's a hydrogen bond. Other properties of water, this causes it to have a high heat capacity. Water changes temperature very slowly. It also causes, in the solid state, water is going to be less dense, less packed, so it's going to float. In the liquid state, it's more dense or more packed. So liquid water, if you have ice and water, the liquid water will sink. Water is also cohesive, which means that molecules cling together. Because of its polar nature, water has the highest cohesion of non-metallic liquids. Water has a high surface tension, which is why bugs can kind of walk along the top of the surface of water, because those molecules want to cling together, and it actually creates surface tension that the insects can walk on top of. A little bit more vocabulary. Water also is adhesive. Whoops, let me make that a which means that they sticks to other substances that are hydrophilic, which means water-loving, or strongly attracted to water. So the reason why this is clinging to the sides of the glass is because it's adhesive. Water is a good solvent, and it's going to dissolve polar and ionic substances in water. So zooming in on this, here's our oil layer, and it's not mixing with the water because this has no charge to it at all. None of the parts of this molecule have any charge whatsoever. We're looking at our water. This has got a slightly negative charge, negative charge, positive charge, and so on. There's a lot of charges going on here. So this is nonpolar, no charges. And water is polar because it has charges, positive and negative charges. Also, water is neutral. It has a pH of 7.0. What that means is we've got just as many positive charged particles as we have negative charged particles. So that's going to mean that it's neutral. Overall, it's going to have no charge, but the number of ions, it's going to be right in the middle where it's 7, so that's neutral. And that's the end of the notes for Friday.